Hey, geometry students, welcome to section 7.4, properties of similar triangles. And so we're going to continue. We learned in 7.3 that there's three ways to prove triangles are similar, AA, side, angle, side, and side, side, side. And so now we're going to look at some other properties of triangles and proportional situations that you can create. Okay, and so there's some funky names and definitions here, but I think you'll see the basic concept behind each one is pretty simple, especially if you know how to write a proportion and solve a proportion. Okay, so our first definition is the proportionality theorem and its converse. Okay, so the proportionality theorem says a line parallel to the side of a triangle divides the sides proportionally. Okay, so let's get a little drawing there of that. So if we draw ourselves a nice little triangle, we'll call them A, B, and C to be very original. So if you take any line and you cut that triangle along one of the sides with a parallel line, so like say we do this, and we'll call the points where that intersects D and E. What you now know is that this side here is cut proportionally to this side, and that, let's get a different color. This side here is now proportional to that side. So if we were to write that out, we know that the distance that is BD divided by the distance of DA is equal to the ratio of BE to EC. No, it's not. Let's erase these because that's confusing. Okay. So in other words, if I were to start to know, if I were to, this is 2, this is 3, and this is 5, then I'd be able to go ahead and find one of these other missing sides because they are now proportional. So anytime you see a parallel line in cutting through a triangle, the little sections of that triangle have to be proportional to one another. Okay, and so the converse of that is simply take the if and the then and switch them, and that is if the sides are proportional, i.e. if they're cut proportionally, then the lines, we'll say the intersecting line, oops, I can spell, are parallel, or we'll say line is parallel. So you can know they're parallel and then know the sides are proportional, or sometimes they'll ask you to say, see if the number sides are proportional, and then that will prove that the lines are in fact parallel. But the biggest thing to know is whenever you see that intersection, those sections, those pieces of the line that are created, of the sides that are created, those have to be proportional to each other. Okay, let's take a look at our second definition. Another great name that probably when you read it just kind of makes your head spin, but we'll just break it down. It's not very complicated. And that is the two transversal proportionality, or two transversal proportionality. What is that? That is if three or more parallel lines intersect transversals, they divide them proportionally. Okay, again, it kind of sounds like an awful mess, but it's not that bad. That basically means if you have three parallel lines or more, it can definitely be more than three. So we have parallel lines. I'll put this one down here for good measure. Okay, and these are all parallel. Then any other line that they intersect, so say I draw a line like that, then that means that this and this are proportional to, say there's another line, and these are the transversals being intersected, that those two green ones, again, would be proportional to these two orange ones here. Okay, so again, let me go ahead and write a ratio, or a proportion, I'm sorry. But let's name each intersection. Let's call this S, T, U, V, W, and X. Okay, so that means your ratio of SV to VW would be a proportional to the ratio, and I'm going to use the colors to set them apart, but TU over UX. And we'll do some problems here in the questions that you'll see how we apply this. But again, when you see the lines are parallel, then you can know that those pieces cut off are in fact proportional to one another. Okay, and last one, angle bisector theorem. This one says that any bisector of a triangle divides the opposite side proportionally to the side lengths of the triangle. So for example, we just draw ourselves a nice little triangle here of any kind. And then if it has an angle bisector within it, so we take this and cuts through there. Doesn't matter where it hits the opposite side, but it's an angle bisector. So I must know that those two angles are congruent because it has to cut it in half. And then what that means is that this side cut off by it is proportional to this side length, and this side length here cut off by it is proportional to that side length. Okay, and again, let's put some letters on here to make sense. Let's go with G, H, I, and J. Then I can write some proportions that would say HI to GH would have to be equal to IJ over GJ. Alrighty, so just being able to write proportions. And again, they all have kind of funky names and circumstances, but for our simple purposes, just realize when you have an angle bisector or these parallel lines, then you're creating proportional segments wherever they're intersecting. And in the questions, we're going to practice this, and that's why I assigned actually four questions to give you lots of practice. So here we go. Questions, we're doing 484, numbers just 1 through 7, so 1, 3, 5, and 7 odd. And so here's number one. They give us this triangle, and you can see this is the proportionality theorem because you have a triangle. It's being intersected by CD. The triangle is EFG, and the lines are parallel, as indicated. So you have these segments here, here and here, and here and here. And so you know that those have to be proportional. And so you can write an equation. And I think the problem, let me just clarify, I think they want us to find DG. So they want us to find this segment right here, okay? So we can write a proportion. We can say, and I'll do it in letters first just to kind of do it on slow on this one, and we'll go faster on the other ones. But in other words, EC divided by CF is the same as ED divided by the one we're looking for, DG. Oops, not DE. Divided by DG. So let's go ahead and substitute in, and we can solve that. So that would be 32 divided by 24 is equal to 40 over what we're looking for. So we'll call that X. Alrighty, so now we just have our proportion. Hope we get very comfortable with solving proportions. We're going to cross multiply. And so that gives us 32X equals 40 times 24, which is 960. Then we just divide by 32. This is why I call it cross multiply and divide. We're going to simplify that. And so X equals 960 divided by 32, which is actually 30. So DG here is 30. So again, even though the name and the kind of the setup and the explanation of the proportionality theorem is complicated, you really just need to be able to know what pieces are proportional to which pieces, be able to set up your four-part proportion, and then you cross multiply and divide. Let's look at another example, number 3. Number 3 is a little different. Here, they're basically doing the converse. They're saying verify that AB and CD are in fact parallel. So this is an example of where we know all the side lengths, but we don't know if the lines are parallel, or where they're asking us to prove that they are in fact parallel. So how would we do that? Well, the initial statement says if they're parallel, then you know they're proportional. This is saying, are they proportional so that we can know they're parallel? Well, how do we find out if they're parallel? Well, I want to see if this piece divided by this piece is in fact equal to this piece divided by this piece. Now, if you're looking at it, this is not a very complicated one because you look at the numbers, and we're going to see it works out very simply. But I would simply say, okay, AC is 1.5 divided by CE, which is 1.5. And I'd ask myself, it's an easy question to answer in this case, is that equal to BD, which is 1.5, divided by DE, which is also 1.5? Well, that simplifies simply to 1. 1.5 by 1.5 equals 1 equals 1. So in fact, they are equal to each other, so the sides are proportional. Therefore, AB is parallel to CD. And if we had to give a reason, we would say the converse of the triangle proportionality theorem. Okay, which just means because we proved that they were proportional, we now know that those two lines must be parallel to each other. Okay. All right, number 5. This is the two transversal proportionality, where again we have two transversals. The first one is here, the second one is here, and you have 3 parallel lines. You can see they're parallel because they do indicate it with a little chevron. And so then they're asking us to find if you look at it's actually a picture. This is a road map. We've got parallel roads cut by these 2 non-parallel roads. And what the question is, they want the distance between Broadway and 34th Street. Well, or the distance between 34th Street and 35th Street between Broadway. So that means they want this piece right here. This would be our X. And so we just set up a real simple proportion to solve this. 275 over X must be equal to 240 divided by 250. Okay? And once you set up your proportion, you can simply cross multiply. And that's going to come out to, let's see, 240x, whoops, 240x equals 275 times 250. Let me just confirm what that is. You can practice your long multiplication if you want to, but it's not what we're focusing on. 275 times 250, that's 68,750. Get X by itself. Now we're going to divide, cross multiply, and divide. So we divide that by 240. And it says we're going to round it to the nearest foot because I'm getting a decimal, 286.45. So that's just going to mean simplified to X equals 286, in this case, feet. Which you can see that's pretty similar to the other values there, so that looks reasonable. Okay, so again, just setting up a proportion, cross multiplying and dividing, even though the numbers are bigger than otherwise, it shouldn't really matter. And the last one, number 7, using the angle bisector theorem. We have a triangle and it's being bisected. We can see that because the 2 lines say they are congruent. And so we know that, based on that theorem, that this side and this side are proportional to this piece and this piece. So we can go ahead and set up our proportion. You can see, although they're different, you're really solving these all the exact same way. Though you can see this time that we're going to work with some algebra expressions, so you'll get practice there. So 6 over 9 has to be equal to y minus 1 over 2y minus 4. All right, how do we solve a proportion? Well, we've done it several times now. We're just going to cross multiply. It'll be a little different because you've got y, so it won't be quite as straightforward as the other one. But we get 6 times 2y minus 4 equals 9 times y minus 1. And so now it's just a straight up algebra problem. We're going to distribute in both cases. And so that comes out to 12y minus 24 equals 9y minus 9. We want to get the y's together, so I'm going to subtract 9. Scroll up a little bit. And so that leaves us with 3y minus 24 equals negative 9. I need to get my constants together, so I'm going to add 24. And so that leaves me with 3y equals 15. Now we're going to divide by 3, and so we get y equals 5. Now check your question. Does it ask you to find y? No, it asks us to find AD and CD. So that just means we take our y equals 5 and we plug it in. Whoops, get my pen here. We plug it in up here and up here at the top. So we want to plug in 5. So if I just do 5 minus 1, that means I get 4 here. And I plug in 5 there, I get 10 minus 4, and so I get 6 right here for AD. All right, so a little more algebra work, but nothing crazy. No quadratics or anything, though we will run into those a little bit in this chapter. And so, again, just setting up a proportion, solving it, and having fun while doing it. So I look forward to talking about this with you in class and helping you however I can. And let's go ahead and cut up some triangles. See you soon.